Hello friends, last class I discussed about the chemistry of the organic semiconductor, or what is the organic semiconductor, how many what is the band diagram of the organic semiconductor, right? Now here I will discuss about the optoelectronics properties of the organic semiconductor. So organic semiconductors have electrical properties, mechanical properties, but it has the strong optoelectrical properties. Okay. Uh, First I will tell organic semiconductor, that I told what is the difference between organic semiconductor and the inorganic semiconductor related to chemistry. So it has the weak van der Waals force. Okay. So organic semiconductor, due to the weak van der Waals force, okay, due to the weak van der Waals force, organic semiconductor can store different kind of the properties for a long time. Okay, now I will discuss about the optical properties mainly. Okay, optoelectronics means it's related to optical and the electrical properties. Okay, now here suppose this is the band gap of the organic semiconductor, this is the HOMO label, and this is the LOMO label. Okay, so the band gap, this is called the band gap between the HOMO and the LOMO. So normally, in case of the organic semiconductor, suppose it has the band gap between 1 to 3 electron volt for case of the organic semiconductor. But in case of the inorganic semiconductor, maximum semiconductors have the band gap of 3 electron volt, 2.5 to 3 electron volt. But various range of materials are there under the organic semiconductors, which has a different kind of the band gap. Okay, and we can also tune the band gap of the organic semiconductor. Okay, band gap of the inorganic semiconductor, we can tune the band gap of the inorganic semiconductor, but it is little bit difficult. But in case of the organic electronics, we can easily tune the band gap of the semiconductor. Suppose in a one semiconductor, the band gap is the 3 electron volt. Okay, so one kind of the semiconductor is the suppose CuPC. Okay, so if you dope any kind of, if you mix any different kind of the materials, or if we use any kind of the, this is suppose p-type semiconductor, if we use n-type semiconductor, we can easily mix n-type semiconductor with the p-type semiconductor in case of organic electronics, right? So for that the band gap can be tuned. So this band gap will be changed from 3 to 2.5 electron volt. So it can detect different kind of the lights. Okay. Now, two different processes are there, transitions are there in case of the optical properties. So first is the we can tune the band gap of the organic semiconductor very easily by mixing of the different kind of the organic semiconductors. Okay. Okay, there are the two transitions, right? One is the lower band to upper band transition, and is the upper band to lower band transitions. Okay, this transition will take place by absorption process or recombination process. Okay, one is the absorption process, another is the recombination process. Two processes are there. Okay, so it's the HOMO, the LOMO level. Okay, first I will discuss about the absorption process. So both the processes are related to transition between HOMO level to LOMO level. Okay, now what is the absorption process of the any kind of the semiconductor? Okay, so in case of the inorganic or in case of the organic semiconductor, if energy, suppose the band gap is this is the band gap, that is suppose 3 electron volt. Okay, so if any light is incident on this semiconductor, organic semiconductor or inorganic semiconductor, the energy of the light should be greater than this gap, E optical, that should be E gap. Okay, this is the light energy, optical energy, and this is the band gap between HOMO and LOMO. If E optical is greater than E gap, band gap, then the electron, because the HOMO, that highest occupied molecular orbital, okay, the HOMO level is occupied by the electron. So when the energy, this energy hits the semiconductor, electron will go from this HOMO level to LOMO level. Okay, here hole will create. So this is the electron hole pair. Here is the electron, here is the hole. These are bounded. These are not free electrons and holes. Okay, these are bounded. So to break this bound electron hole pair, I have to apply the external electric field or internal electric field. Okay, so if this energy hits the semiconductor, the electron hole pair will create. This is called the absorption process. By absorption of the photon, photon means the light energy that consists of photon, right? So by absorption of the photon, electron hole pair will produce inside the organic semiconductor or inorganic semiconductor. Okay, then this process is called the absorption process. But two kind of the electron hole pair can produce in case of the organic semiconductor. One is the singlet electron, right? Another is the triplet. Okay, so this is called the singlet electron, that is the direct transition from HOMO to LOMO. Okay, so due to this electron hole pair, one kind of the absorption peak I will get. Okay, that absorption curve I will discuss now. Next is the triplet electron hole pair or triplet exciton. When it will produce, so this is normally higher energy level is the lower energy level. So if in case of the organic semiconductor, there are lots of trapped states are there. Okay, so if any transition occurs between higher level, okay, higher level to next higher level, then triplet exciton will create. Okay, that means the the photon will be absorbed by the higher energy level of the organic semiconductor. Okay, this is the normally this is known as the ground state. This is the excited state. If the photon is related to exciton is related to excited state, then triplet exciton will create. Okay, triplet exciton. Suppose this is the one energy level. Lots of energy levels are there. Okay, so if transition occurs between higher energy level to next higher energy level, then triplet exciton will create. Okay, so two kinds of excitons are there. One is the singlet, another is the triplet exciton. Okay, now I will draw the absorption curve. Okay, this axis is the related to wavelength, or you can consider as a band gap, and this energy is the absorption. Okay, unit is the per centimeter. Okay. In case of the inorganic semiconductor, if you see the absorption curve, this is like normally exponential curve. Okay, that means here one lambda is there. Suppose lambda is there here 400 nanometer. Okay, it's up to 1000 nanometer. Now we can see here I am getting the absorption peak at 400 nanometer. Okay, in case of the inorganic semiconductor, the maximum inorganic semiconductor shows such kind of the behavior, such kind of the exponential kind behavior. Okay, maximum inorganic semiconductor shows exponential kind behavior. Okay, so it has one band, it has only one band gap. Suppose corresponding to 400 nanometers, suppose 3 electron volt band gap. Okay, 2.52 3 electron volt band gap. Maximum inorganic semiconductors have this band gap. Okay, that's why we will get such kind of the exponential behavior for case of the inorganic semiconductor, right? Only one transition will be there. Okay, now If I tell about the absorption curve of the organic semiconductor, okay, alpha. So you can see Gaussian like behavior, okay, like behavior. Maximum in organic semiconductors show such kind of the behavior, Gaussian like behavior, okay. So from this graph, what we can predict, okay, you can see two absorption peak. You can see two absorption peak. One absorption is due to the creation of the singlet electron hole pair, another absorption is due to the creation of the triplet electron hole pair, okay. So this is the lambda. This curve is this axis is related to lambda. So there is a relationship between band gap and the lambda is equal to AC by lambda, okay, or E is equal to 1240 by lambda, while lambda is in nanometer. So from here we will get the band gap, okay. Suppose you know this lambda. Suppose this is 500 nanometer. This peak we are getting this peak at suppose 700 nanometer. Okay, for 500 nanometer I will get one energy, okay, band gap, okay. Suppose here I am getting suppose 3 electron volt I am getting for 500 nanometer. Here I am getting 1 electron volt for 700 nanometer, okay. That means suppose the band gap between the particular organic semiconductor has 3 electron volt, okay. The band gap between HOMO level to LOMO level. Okay, there is another band gap between this HOMO level to LOMO level, that is the 1 electron volt, okay. That means this is related to triplet exciton and this is related to singlet exciton. There is one trap level or an extra and inter-system crossing level between HOMO level to LOMO level. Due to this we are getting the triplet exciton as well as the singlet exciton. So maximum organic semiconductors show such kind of the Gaussian like behavior. More than 2-3 peak we will get. So if we mix another material, we can see the another peak, okay, in the absorption curve. Lots of peak we can see if we mix. So multiple band gap will create, okay. Now coming to the recombination process, okay. Absorption process I have already told. So now I will come to the recombination process, okay. Recombination, that process is also related to singlet exciton and the triplet exciton, okay. The recombination means in a system suppose free electrons are already there in LOMO level, okay. So free electrons are already there in the LOMO level. By applying voltage we can create the free electrons, okay, inside the system. So these electrons are there. Now after certain lifetime, okay, the electron will fall down to the HOMO level, okay. There I will get electron. This transition create the radiation. When electron will fall down from LOMO level to HOMO level, then there will be a radiation or system will emit one radiation, okay. So from this radiation, this one kind of the wave will get. So this wave has one particular wavelength, okay. Now if when the singlet, so that time we will get the singlet, okay. So when singlet means the electron, there is a direct transition between LOMO to HOMO, okay, that is related to singlet exciton, okay. Now that time we will get one radiation. This is known as fluorescent, okay, fluorescent process, okay. When the recombination process is associated with the singlet exciton, that process is known as the fluorescent process. So we will get a suppose one wavelength, that is the 400 nanometer I am getting. During the fluorescent process I am getting one wavelength, okay. I am getting one radiation which has this wavelength, 400 nanometer wavelength, right. Now in case of the triplet exciton, what will happen? So triplet exciton, how the radiation process will take place in case of the triplet exciton, okay. Triplet exciton means, so in case of the triplet exciton, the transition between another energy level to the ground state or HOMO level. Okay, so in case of the singlet, direct transition from this LOMO to HOMO. But in case of the triplet, so first electron will fall down from LOMO to one intersystem level, and from this intersystem level to this HOMO level. Okay, then radiation will take place. Okay, this process is called the phosphorescence process. Okay, this phosphorescence process that is related to triplet exciton. Then the exciton, the electron will directly fall to the HOMO level, but not from LOMO level. It will fall from the another level to the HOMO level. Okay, then the phosphorescence process will take place. Okay, this process is known as the phosphorescence process. Okay, so that time suppose we will get a one wavelength which has lambda 600 nanometer. Okay, so for recombination process also we will get a different kind of the light from the same system. Okay, so same system can produce suppose green light, and same system can produce the red light. Okay, due to the singlet exciton and the triplet exciton in case of the organic semiconductor, because the organic semiconductor has multiple levels. Okay, or multiple inter levels are there. So this is the fluorescent process and the phosphorescent process due to the singlet exciton and the triplet exciton. Okay, there is another process in any kind of the semiconductor, that is the non-recombination process. So these two processes are known as the recombination process, and there is one process that is the non-radiative recombination process. Okay, non-radiative recombination process. So when there is a transition between higher level to the lower level, okay, so I am getting one wavelength, okay, right? So I am getting photon, okay, but non-radiative recombination means that is related to the phonon only. So emission will take place, but this emission consists of the phonon, okay, instead of the photon. So we will not get any wavelength light. Radiation is there. The radiation, we will get the radiation in the form of the heat energy, not in the optical energy. Okay, same process is there. No direct transition is there. Okay, there also the electron will fall down from higher level to this inter level, and this inter level to this lower level. Okay, but this is related only the phonon, heat energy. Okay, when we will get heat energy instead of the optical energy from the system, so that time the performance of the system will be reduced. So suppose for case of the photodetector, I should get the high efficiency. Okay, so but in case of the, if maximum electrons are associated with the, we are getting the phonon from these electrons, so then the device performance will be reduced, or we will not get the maximum efficiency from the organic semiconductor based devices. Okay, so this I have discussed about the normally optical properties of the organic semiconductor. So that I told that in case of the absorption, first the electron hole pair will produce in terms of the singlet and the triplet. After production of the electron hole pair, then this electron hole pair means exciton, then how the exciton will transfer through the system, that I will discuss on the next class. Thank you.